Welcome to the next lesson in the course. Now that we've had a chance to talk about lambda expressions, and I've given some examples of method and constructor references, we're going to talk about functional interfaces. These features represent some of the key foundations for Java 8's concurrency and parallelism frameworks, and they're also useful for many other types of functional programming applications. In addition to giving an overview of these features, I'll also show how these Java 8 features are applied in a number of concise example programs, which you can download from my live lessons repository in the GitHub account. Let's start by giving an overview of common functional interfaces. A functional interface contains one and only one abstract method. Examples of functional interfaces that you're probably familiar with already would include runnable with the run method and callable with the call method. In all these cases, there can be only one, just like the Highlander movie. A functional interface is the type that's used for a parameter when a lambda expression or a method reference is passed as an argument to a method. Here's an example that's available online. This method, called runTest, is used to test various implementations of a factorial interface. As you can see here, function fact is passed as a parameter to runTest, and function will be parameterized by two parameters, a type that's passed to the function and a return value that's returned back from the function. As you can see, when this is called with a value n of type t, it goes ahead and it applies n to the factorial function. Down here we see how this runTest method is actually used in practice. In this case, we're passing in the parallel stream factorial method as a method reference, as well as the value n. The implementation of this method is shown down below. It essentially goes from all the numbers from 1 to n, inclusive, running in parallel, computing each of these into a big integer, and then calling the reduction operation, which goes ahead and will multiply all the values together until it creates the big integer factorial as the result. We'll come back and look at this function later on. The main thing I want to show here was just the use of passing method references, or lambdas as the case may be, as a parameter to the runTest function. Java 8 defines many types of functional interfaces. Many of these are represented in terms of various operations, things like BiConsumer, BiFunction, BiPredicate, function, predicate, and so on. And we'll take a look at many of these in just a minute. There's also a number of specializations of the functional interfaces that are going to work with primitive types. That's one reason why the list is so large, because the function interface has to support both reference types, which are defined by users, as well as primitive types. We're going to focus on 5 of the most common types of function interfaces: predicates, functions, BiFunctions, suppliers, and consumers. All of the functional interfaces that we'll be describing and illustrating in the upcoming examples are all stateless, which means that they only take in what's passed as a parameter or parameters into the function, and they return a value. There are no other side effects that are used. There's no mutable state, which is important when trying to write code that will work without change in both sequential and parallel use cases. We'll start by giving an overview of the predicate, function, and BiFunction functional interfaces. A predicate is an interface that performs a test that returns either true or false. As you can see here, predicate is an interface parameterized by type t, and it defines a single method, test, that takes a parameter of type t and returns Boolean. Here's a simple example, which you can download from my website, that illustrates how to use the predicate interface. In this example, we're going to combine the use of the predicate interface with the concurrent hash map, which is a hash map that supports so-called atomic operations, those that you don't need to be worried about corrupting the internal state of the hash map, because they're going to be thread safe and properly synchronized using various clever mechanisms such as compare and swap. We're going to put into the concurrent hash map 3 entries for the 3 stooges: Larry, Curly, and Mo. And we're also going to associate IQ points with each of the stooges, which, as you can see, are rather low because they weren't very smart. So we go ahead and we make our IQ map, which maps string to integer. And then down here, I show how the removeIf method, which is a method that's defined on the map entry set result, which goes ahead and will take a lambda expression that deletes any entries with an IQ that's less than or equal to 100. So you can see here that we call removeIf, and that will then figure out that this is actually going to be taking an entry, which is a key value pair, and we're going to go ahead and set the value, remove any entries where the value of an entry is less than 100. In this case, entry is actually a shorthand for entry set with the name entry. So entry set would be the type, entry would be an instance of that type. And we can use the shorthand because Java 8's compiler supports advanced type inference capabilities, which can deduce the types from what you're passing in. So it knows that this, for example, is taking an entry set. So it knows that entry is in fact an entry set. Here's what it looks like if you take a look under the hood. If you go and you take a look at the concurrent hash map class, you'll see it inherits from the collection interface. And if you look in collection, you'll see it has a default method called removeIf. And this will be passed a predicate called filter. And then you can see in the code how this filter will be used inside the implementation of removeIf. If you recall, the removeIf method is being passed a lambda expression that says entry.getValue less than or equal to 100. And of course, this is a predicate lambda that's going to return true if the element is indeed less than or equal to the value 100. If you take a look at how this is actually used inside the removeIf implementation, there's a check in here that says if filter.test, and then it's passed each.next, which is the actual item to work on. So what that's really looking like, if you were to kind of step back and see what the compiler sees, is it would say, if the next item that we're iterating over has a value of less than or equal to 100, then go ahead and call remove on that item. And so what it's essentially doing is it's replacing that in the test, and then it'll use that to decide whether to keep or remove a given entry. Let's now talk about the function interface. Function is a very common interface that's used quite widely in Java 8, especially Java 8 streams. And what it does is it applies a computation on one parameter and returns a result. So as you can see here, unlike predicate, which only took one parameter, function takes two parameters, t and r. When we look at the apply method, which is what it's using to interact with the outside world, t is passed as the type of the value to the apply method, and r is the return value returned back from that. Once again, we'll use the concurrent hash map to demonstrate the function interface. In this case, we're going to define what's called a memoizing cache. And this cache will essentially map integer to integer using the concurrent hash map. And what it's going to do is it's going to be a cache of numbers and an indication whether those numbers are prime or those numbers are not prime. What will be stored in the hash map is the candidate number, and if it's a prime number, the map value will be 0. If it's not a prime number, then it'll indicate the smallest factor that can be used to divide the number evenly. So let's go ahead and take a look at how this would work. As you can see here, after initializing the prime cache, then when we want to compute a new prime candidate, which is just some arbitrary number, we go ahead and call compute if absent, and we pass in the prime candidate, and then we also pass in a lambda or a method reference. The compute if absent method is a special atomic check then act method that's defined by concurrent hash map. And what it means to be atomic means that even if multiple threads of control are simultaneously calling compute if absent on multiple cores within an application, this value will only be computed once, and the value will be done in a way that does not actually corrupt the internal state of the hash map, which would otherwise be possibly subject to race conditions if we didn't use an atomic check and act method like compute if absent. Under the hood, when we pass this in, the lambda expression says we'll take the key, which is the prime candidate that's passed as a parameter, and we'll then call the prime checker method with that key as the parameter, and that will then go ahead and call a function. And of course, this function will be defined with the functional interface. So prime checker, as you can see down below, matches the functional interface where it takes a prime candidate as one integer and then determines if the number is prime and returns an integer back as a result. There's a couple of different ways we can do this. One way is to pass a lambda expression. We can also pass this : prime checker as a method reference, which is a more concise way of expressing that we want to have prime checker be used to determine if the prime candidate is indeed a prime number. Now, if you were to take a look under the hood at the computeIfAbsent method that's defined in concurrent hash map, you would see it's passed a function that we just talked about, which is called mapping function. So it takes a key as one parameter and a mapping function as the second parameter. And then if you look inside the implementation further, you could basically see the following. So the mapping function, of course, will be passed whatever the parameter is, which in this case was the prime checker method, which matches that function interface. And so that's passed in there. And then down here, we have the code of computeIfAbsent saying mapping function dot apply, passing in the key. And that will, of course, expand in the underlying compiler to actually be a call to the prime checker method that was passed as a parameter via the mapping function parameter. So what will happen in this case is it'll go ahead and look it up. And if it's already there, it'll return it right away from the hash map. So there won't be an expensive prime number computation. Otherwise, the first time we call this, it'll do the expensive computation to compute whether a number is prime, either returning 0 or the smallest factor if it's not prime. And then that will get stashed away inside the concurrent hash map and be used for subsequent values. So in effect, the apply method is being replaced with the prime checker lambda function. Let's now take a look at a BiFunction. A BiFunction, as the name suggests, is a function that applies a computation on two parameters. That's what bi means in this case. So it's going to apply it on the parameters t and u, which could in fact be different, and it returns a result of type r. This is what the apply method looks like. It takes t and u as its two parameters in that order, and then it returns r as the return result. We'll go back again and describe our IQ map, which we used for our Three Stooges, which, as you recall, has Larry, Curly, and Moe. And although they're given low IQs to begin with, this particular piece of code is going to subtract 50 points from them because we've determined through some IQ test that they're even dumber than we thought they were. There's a couple of different ways we can do this. One way to do this, the conventional way of subtracting, say, 50 points from each person in a map, is to use the Java 7 for each loop, where we're going to iterate through every element in the map's entry set, which comes back as key value pairs, where the key is a string, which is the name, and the integer is the value, which is the integer. And we're going to basically say entry.setValue to be the result of subtracting 50 from the value of an entry. So that's certainly one way to do things. There's two problems. First of all, this code is somewhat tedious to write. It's somewhat verbose. And secondly, it's not atomic because it's going to be making a set value call and a get value call. And this is mutating. And as you can see, there's no locks being held here. So this code is going to be subject to race conditions if run on a multi-core processor with multi-threading. The alternative approach is to use replace all with a BiFunction lambda. And what we do here is, because it's a BiFunction, it receives both a key and a value. So that's what open paren k comma v close paren means. It's taking two values here. And what we're doing is we're subtracting 50 from the value, and replace all will essentially take that result and update the value in the map for that particular key with the old value minus 50. Unlike the entry operations, however, replace all will operate in an atomic thread-safe manner. So not only is it more concise, but it's also going to be thread-safe and very efficient as well. Here's what the code looks like. If you were to peek under the hood, you would see that replace all is going to take a BiFunction where it's going to have the key and the value. And then internally, of course, when we call this replace all method, we're going to pass the lambda expression where we're going to say the value will be updated to be value minus 50. Notice we don't actually use key explicitly here, but that it's going to work on the key, which is value parameter k, by virtue of the fact that that's the particular key that we're operating on. We don't have to use the key in order to update the value, however. And that's just the way this particular implementation works, or this particular example works. So the BiFunction parameter is bound to the lambda expression v minus 50. And then if you take a look down here in the implementation of replace all and concurrent hash map, you can see how calling function.apply, which is what the code does, is going to end up replacing the old value with a new value, where the new value is going to be the old value minus 50. And then you can see after that's done, we take the new value and then we call replace node to replace the value at that key with the new value. So the old value is replaced. So that was basically some of the most common examples of functional interfaces: the predicate, the function, and the BiFunction. What I'm going to do now is give you an overview of two more very common functional interfaces: consumer and supplier. So a consumer is a functional interface that accepts a parameter and returns no results. As you can see here, consumer is parameterized by type T, which is what it will be accepting. And its accept method will simply take a value of type T and do something with it. But as you can see, because the accept method has a return type of void, there'll be no value coming back from consumer. So consumer is commonly used for a variety of purposes where you want to pass a value in. So here's an example where we can use consumer. We're going to make ourselves a list of threads, and we're going to have 3 threads in that list. And we're going to give the threads names. We're going to call them Larry, Curly, and Moe, because we're in a Three Stooges mood. And so those are going to be stored as a list of threads. Notice, by the way, these threads have not been started yet. We could start them, but right now we're just going to go ahead and do some other things with them in that list. And of course, you can download this example from my website. What we're going to do here is we're going to show how you can use the for each function, which we talked about earlier, in order to be able to print the values that are in that list. So as you can see, for each is going to be passed a parameter, which is actually a method reference to system.out println. So we're passing this in as a method reference, not making a function call or a method call. We're passing in the method reference to the for each method. Now, if you were to peek under the hood at how for each worked, here's what you would see. For each is actually defined as part of the iterable interface. It's a default method that's defined on every iterable unless you decide to override it for some strange reason. And what it does, as you can see, is it is passed a consumer, which is given the name action. And then in this case, that's going to be the system.out println method, which conforms to that consumer interface. So it's essentially bound. We're binding println to what's being passed into for each. And then it's going to iterate through every element that we have. And we're going to go ahead and call for every element that we have in the iterable. So it'll iterate through every element. And for each element T of type T that's available as part of this interface implementation, we're going to go ahead and call the accept method with the value T as the parameter to accept. So what that's doing, of course, in this example is it's printing out each element, each name of the thread, because the thread has a name like Larry, Curly, or Moe. That's being printed out when accept is called, because that is ultimately being implemented by system.out.println. This example can also be can be used to illustrate the use of a function. So we're going to show how functions are used to do another thing that we show with this simple example. In particular, we're going to sort the threads in the list by their names. So we'll end up with Curly, Larry, and Moe if we sort them in ascending order. And the way this is going to work is we're going to pass in a method reference to the method that we want to use to get the name of each thread. So of course, there's a method called getName that's part of each thread, and you can use this in order to get the string name. And we use this essentially as the comparator for the sort method. So there's a comparator.comparing method that takes in a method reference, and it uses it when we're doing the sorting. So let's take a look at this and see how it works under the hood. This is part of the comparator interface that's part of Java, the Java class library. And so what you see here is the comparator has a method called comparing, And this method takes a function, and it's used to, it's called key X for key exchange or key comparison. And so what we're going to do here is we're going to, or the way it's written, we're not doing this. This is part of the Java library. The comparing method is going to use this to compare the two parameters that are passed here, C1 and C2, which is what we're comparing, the two values. And we're going to apply whatever method is used to extract out the part of the parameter that we want to compare based on. So in this particular case, what's passed in as key X is thread : get name. That's the method reference that's bound to the key X parameter. And so that name will then be used when key X.apply for C1 is compared to key X.apply to C2. So if we were to kind of expand that out and see what the compiler sees, we would see that C1.getName is then being compared to C2's getName. And that is what the sort routine is using in order to decide how to order any two elements that it's trying to sort. The final functional interface we're going to talk about is called Supplier. Supplier returns a value and takes no parameters. So it's almost the inverse of consumer. Remember, consumer took a parameter and returned nothing. Supplier, in contrast, is going to take no parameters and return a value. So it's a generator of values. As you can see, it's parameterized by type T, and it has a single method in the interface called get, and that returns a type T. Let's take a look at an example to make this more clear. We'll actually look at a couple of examples. The first one is just a supplier interface. The second one's going to be a constructor interface that's used for constructor references. So in this example, we're going to create ourselves something called a being map, which maps string to string. And that will just be a simple hash map where we go ahead and put a mapping between strings, where they're names like demon or angel, and then their characteristics, naughty or nice or whatever. And as you can see in this example, we're going to show some other interesting features of Java 8, namely the use of optional. And what this is being used for, when we get through all the examples here, is we're going to use the or else get method, which is defined on optional, in order to supply a default value if somebody looks up a being who doesn't have a characteristic in the map already. So if we make ourselves a new being with whatever, let's say it's going to be a demigod or a monster or whatnot, then we're going to go ahead and put that in there. We're going to look it up in the being map to see if we've already got a being with that type. We get back what's called an optional, and we can then go ahead and say down here in the print statement, where you see the red highlighted text, the disposition of the being is disposition.orElseGet. And if there was actually a being there already, we'll get its disposition. If it was demon, we'll get naughty. If it's angel, we'll get nice. However, if there was no being under that name, if we put demigod in, for example, that's not in our map, then we would go ahead and use the reference that's passed in here, that's the unknown value. So if there's nothing that's given, in other words, if we have a being who hasn't been entered to the map already, or else get will simply return unknown, which is essentially a supplier. And so if you take a look at or else get, you can see it takes a supplier as the parameter, and it uses that. So in this case, we'll pass unknown if there's nothing else that's already registered under that name. And the string literal unknown is the one that's bound to the supplier lambda parameter. And what's going to happen here is if there is no value on that entry in the optional, then we're going to go ahead and return other.get, and that'll of course return the string unknown. So that's essentially what is happening here, and that's an example of using a supplier. There's also ways of using suppliers for so-called constructor references, which turn out to be useful for a whole variety of different factory patterns. Here's a simple example that you can get from my GitHub account. In this case, we're going to have something called CRDemo, which is a class with a main method. And what it's going to do is it's going to define a constructor reference, or rather a supplier, that will hold a constructor reference in it. So the supplier is parameterized by CRDemo, and then it's going to be assigned CRDemo : new. And that is essentially what's called a constructor reference. So we're going to store that into the supplier. And then in the next line, when we say supplier.get, that get method will actually forward to the constructor reference, CRDemo new, that will allocate a new CRDemo object, and then we will call the hello method on that object, which of course we'll simply call the hello method defined here to return the value hello, which we print out. So that's an example of using a supplier as a way to hold a constructor reference and then make an instance of that object that the constructor reference is associated with. So that's basically the key discussions we're having about the various kinds of core common functional interfaces, predicates, functions, BiFunctions, suppliers, and consumers. And it turns out that these are the common methods you see most usefully applied in the Java 8 streams framework for both parallel streams and sequential streams. And they also get used in other parts of Java we'll talk about later, such as completable futures. Before we wrap up this lesson, though, I want to talk about one more thing, which are other properties of functional interfaces. So it turns out that when I said before that a functional interface can have one and only one abstract method, that was actually a bit of an exaggeration. It turns out that there's another circumstance under which you can have abstract methods in functional interfaces while still considering them functional. In fact, you can have other kinds of methods in functional interfaces. So let's talk about the different types of things you can have here. And we'll use the comparator interface to kind of drive this discussion. It's one of the things you can get out of the Java class library. So here you can see the compare method, which is the functional interface method. That's typically the one you want to override. So that's kind of a no-brainer. That's an abstract method that you have to define. Notice it's not default, it's not static. You have to provide an implementation of that. There's also a couple of other examples, however, here that do have implementations. For example, reversed is a default method that will reverse the sense of the comparison. And reverse order is a static method that will also be used to reverse the way in which the comparison is done. So you can see that even if something's a functional interface, it's possible to have default methods. It's also possible to have static methods. And you can see that the implementations are provided. The default methods, these features are now new with Java 8. There's also one other interesting kind of method shown here, which is the equals method. And equals is an abstract method that overrides a method in java.lang.object. As you recall, java.lang.object is the root superclass of all the reference types in Java. In other words, all the non-primitive types. And so as a result, it's always possible to override those methods, but they do not count as part of the abstract method count in a given interface. So just because you can override equals doesn't make your interface non-abstract, as long as there are no other abstract methods that do not get inherited from java.lang.object. That's a little quirky, and so you might want to read the documentation to see a little bit more about why that's the case. So this then ends our lesson about Java 8 functional interfaces, and we will see lots more examples of how they're applied later in this course.